So let's consider the following example. Suppose we have eigenvalues lambda 1 to lambda k, different eigenvalues of a matrix A. And let V lambda I, where I runs from 1 to k, denote the eigenspace of lambda I, and let Bi be a basis of the eigenspace. So Bi essentially is comprised of eigenvectors of lambda I. Now Bi might have many vectors in it. And now let's take the union of B1 to Bk, right? I didn't write this explicitly, but I runs from 1 to k. So prove that this B over here is linearly independent. And we may use the fact that we have a direct sum decomposition of the eigenspaces. Now notice that the Bi, each one is a basis. So within B1 or B2 or B3, they're linearly independent. But in the general, if you take a union of linear independent bases, you don't always get something linearly independent. So this involves a little bit work, but basically this direct sum pretty much solves everything. So let's see a solution. Okay, so in order to proceed, we need some notations. So let's say B1 is comprised of some vectors. Say V1, V2, up to some point, right? We don't know the dimension. Up to, say, VK1. And up here, let's put an upper index of 1. Okay? So that's B1. B2 will be the same thing, but with an upper index of 2. And so on. So if I want to write out B2, then we'll write V1, 2. So that means this is different than these. We just need some way to denote this, right? It's not beautiful. It's not beautiful, but it's correct. And here, see, we don't know how many elements are in B2. And I can't write K for this and this because there might be a different amount of elements. So I'll just write K2. Up here, I'll write a 2. And more generally, Bi will be of the following form. So V1 up to Vk, where we use an index I to differentiate between, to tell the difference between each basis B. So so I and I, and here it's Ki. So and this means that I runs from 1 to k. So this is redundant here. I just wanted to work concretely, but really what we want is this, okay? If we substitute 1 here, we get B1. If we substitute B2, we get B2, and so on. So we really don't need this part here, and we can just write this. So let's denote. I mean, we already have the notation. Okay, denote, or maybe it would be better to say let. And therefore, the union, right, B is the union of B1 to Bk, right, is just something not really pretty. Okay, it's basically the B1 part, right? So the B1 part would be all of this with index 1, followed by the same expression with index 2, until we finally get to index k. See, that's not really great. So I don't want 2 k's. So what I prefer, maybe we'll change this k over here to an L. Because I don't want, we have a k already over here, so that might lead to some confusion. So let's use L. So we complete the union over here, right? Where we replace I with L. The difficulty here is that it's just a little bit abstract. Okay, it's a little bit abstract, so the notations are not are not beautiful. Okay, LK. How many elements are in the basis BL? LK. What is LK? Well, we don't really know, but it's some number, some natural number. Okay, great. And now they want us to prove linear independence. So let's prove linear independence of B, which is the union of the B1 to BK. So that means we must solve the following. So lambda 1, 1 times V1, 1. So this will be just some scalar up to lambda 1, lambda L1, 1 times V2. See, it's very confusing. VL. So this is corresponding to the first part, B1, plus almost the same thing, right? Lambda 1 K times V1K. And actually we should have, yeah, that's correct, plus, but there's a lot of terms in between that we didn't write. Now I'm going to write this in a better manner, right? I'm going to use sigma notation because this is almost impossible to read, right? It's very hard to decipher. Finally, times this. And it's really easy to make a mistake here. So we're comparing this to 0, the 0 vector, and our goal is to prove that all of the lambdas are equal to 0. But I want to rewrite this in sigma notation. So in sigma notation, which I believe is better in this case, what we want is we want to sum over each of the each basis. So we have sigma I goes from 1 to K. And then we want each of these, right? This part, things in between, and this part over here. So let's think about this part first, right? So that means we have another sigma. We have another sigma. And I want to describe this. So I could use an index J. Goes from 1 up till where? Up till L1 or L2 or LK. So up to L, and it's really worth thinking about this, Li. Let's see if this makes sense. If I equals 1, we're running from 1 to L1, which will give us this. If I equals 2, we're running from 1 to L2, which would give us something that appears here. If I equals to K, we're running from 1 to LK. So the indices make sense. Okay, the indices make sense. And now we want to describe a generic term here. So we're going to need some lambda, and we're going to need some vector v. Okay? And we're going to need an indice that's running from where? From 1 to L1, or more precisely to Li. So that has to be a j. The j's are down here, right? The j's run up to L1, right? L1 might be a billion, or Li more precisely, or it might be the number 1, right? Maybe we only have one eigenvector for a certain eigenspace. And then what about this upper index up here? Well, the upper index, notice the following. This part over here pretty much describes k equals to 1. In between we have k equals to 2 and so on. And this describes, yeah, just describes k. Okay. But what really is important here, what's really important here, and this is the key point, this belongs to the eigenspace of lambda 1. And this over here belongs to the eigenspace of lambda k. How come? Because these are vectors in B1, which is here. And this is just a linear combination. Okay, so finally, let's finish writing this out. So up here, we should have I. And the same goes over here. Let's see if that makes sense. So if I equals to 1, we're over here, and we're summing from 1 to L1 over here in the lower indices. If, say, I equals to k, then we'll have k's up here, just like we do over here. And the indices of j will run from 1 to lk. And we're comparing this to 0. Okay, so let's take a quick break now and try to solve the problem on your own, because we pretty much set up the correct formulation for our problem. So have an amazing day, and we'll see the solution next time.